So we've developed two, let me get my,
Oh, sorry, I started recording.
that's it. We're recording, excellent. Okay, we'll come back to this page in just a second. Get the PowerPoint up and running a little bit. Okay, so at University of North Carolina, and so I normally like to walk all over the room. It's gonna be very difficult for me to stay put, but I'm trying to stay put in front of my camera for the people on Zoom. At University of North Carolina, over many years now, beginning in 2008, well, actually, if I go all the way back to the beginning, back in 2004, we started deploying our first fully automated robotic telescopes. We've grown into probably the second largest robotic network in the world after Las Cumbres. The telescopes, 5 countries, 4 continents, optical, and a little bit of radio with more radio to come. And we started developing curricula to go with these telescopes. Telescopes are used for all sorts of research purposes. I'll outline some of that, but we started developing curricula. And these are curricula for our undergraduate students. We also have a number of curricula that we've made through partnerships with others at earlier levels. We have curricula, everything elementary school through grad school, but some big efforts at the middle school and high school level. But I'm going to be presenting some of our undergraduate work, which I've been most involved with. Okay, and the 2 curricula are called OPUS and MWU. OPUS stands for Our Place in Space. And we first deployed this at UNC Chapel Hill in 2009. And it's now been adopted by 24 institutions, about 3,500 students per year. And I was talking with Michael Fitzgerald last night, and that computes out to like 1.5% of all students in introductory astronomy classes in the US. And so I didn't realize we had, that's not nothing, that's something. And that's something that we hope to grow from. We have a large grant from the National Science Foundation, currently $2 million, to grow this into closer to a national curriculum. And I'll be giving a talk about Our Place in Space tomorrow. It's kind of the intro of these 2. Recently, we got a grant from the Department of Defense, which sounds strange. Why is Department of Defense interested in astronomy education? But they have a vested interest in a STEM educated workforce. They need that desperately. And so this is from DoD Education and $3 million. And they have us developing a follow-up curriculum to OPUS. So the 5 workshops that we're giving, 1 is on OPUS and 4 of them are on this new curriculum. And they've all been scheduled kind of out of order. This would be the 5th one that I would have given. So we're going to learn to run first and crawl second. So I do hope you come to some of the other workshops. Okay, so let's take a look at, I meant to be on that slide. Let me hop down this slide. Tell you what we're going to do today. And do is the right word. I see you brought your laptops. You got a laptop?
Yeah, it's up there.
Okay, good enough. And hopefully those of you at home can do some of these things on your laptops as well. So we'll begin with registration to the Skynet system. It's pretty easy. I'll put up a link and you'll fill in an email address, and within a few minutes, you'll have access to the Skynet telescopes. While you're completing your registration, I'll tell you a little bit about the Skynet radio telescopes. And if you want to learn, we're really an optical network of telescopes. If you want to learn about that, do come to the other workshops. I'll breeze over that today to tell you about our new expansion into the radio that I'm very excited about. I'll briefly talk about the OPUS and MWU curricula and the kinds of things we tackle in them. And then we'll do some of the activities that we've developed for MWU with the radio. We currently have 1 radio telescope, soon half a dozen more. And the kinds of things you can do in radio. Radio is important. we're so used to teaching our students optical astronomy because that's what's available. We have our optical telescopes on, almost every campus has an optical telescope or small telescopes you can take out and do laboratory activities with. But very few people have access to radio telescopes. They have to be in very remote locations. They're very expensive to observe, but it's the other astronomy you can do from the ground. And you can learn a lot about the universe by visualizing it in a different way. You put the two together, and I find it to be a very powerful teaching tool. I've been teaching educational radio astronomy, although I'm not a radio astronomer professionally, since 1992. I run a week-long program at Green Bank Observatory. And so a lot of this new curriculum is based on that. Anyway, the things you can do in radio are timing, spectroscopy, and mapping, for the most part. There's other things, of course. So under timing, we'll do a pulsar activity. I'll show you how to observe pulsars. Under our current Skynet system, we're about to do a once-in-a-decade upgrade, in part to accommodate the radio telescope. So this is something that's been sandwiched in our Skynet 1 system. It will be much nicer in about a year, but it does work. Spectroscopy. So we'll take an on-off spectrum of an edge-on spiral and see some of the physics you can do from that. Now, of course, your data may not come back right away. I'll show you how to put the observations in, and then we'll use data I've already collected so you can see how to analyze it using some of the tools that we've built. Skynet, it's not just about building the hardware of the telescopes, but most of our effort is actually software, trying to develop software platforms that make tasks that used to be really complicated very easy to do. If you can take out the technical difficulty, that hurdle, you can do these things at the survey level. Often at the survey level, you're teaching Astro 100, Astro 101, whatever you want to call it, tour of the universe, greatest hits of the past 400 years, but then they go out and do laboratory activities that are fairly disconnected. If you're dealing with small telescopes or even a campus telescope, they may be doing some things, but it's fairly disconnected from the greatest hits of the past 400 years. But with our global telescope network at some of the premier sites and now radio, you can do the exact things you're teaching them in class. And through the software, we've made it easy enough that survey students can do this. At my institution, they had to redesign the advanced observing class because they were doing all of it and more at the survey level. Anyway, the third thing, as I said, is the mapping. And we've developed some really sophisticated software. I would be so bold as to say it's the most advanced software out there for single dish radio mapping, which is like saying we're the world's expert in something nobody does. Because if you want to make a picture in radio, use an interferometer. And we're not trying to do interferometry with survey level students, but there's still lots of amazing things you can do with single dish and with mapping. And there's a lot of powerful aspects of that because the students, they come with some intuition based on what optical astronomy is, what an optical telescope is. It makes a picture, and then they also build up toolkits, particularly in our curricula, around the optical telescopes. By making use of doing mapping and turning them into pictures, then they can apply that same intuition, that same skill set. And for years, I've been trying to make radio educationally as much like optical as possible. In terms of spectroscopy, it's far easier to get a spectrum in the radio. Anyway, I'll show you how to map a bright source. And you can, of course, do large regions, more complicated, eats up more telescope time. So today, I'm just going to give you enough time to do a little patch around a bright source and show you how we process that and show you some ways we try to bring color into the radio as well. Our MWU curriculum is really about the physics of color. If there's time, I'll talk about a capstone activity with galaxies that combine the optical and the radio. Anyway, that's the plan. All good? Okay, hope you're good online. So first thing is registration. I'm going to close the PowerPoint and bring up this other document. It has the link on it, so do not fear. Here it is. So go to tinyurl.com/skynet-register-radio. And I see some of you have begun to put your email addresses here. Even if you already have an account with Skynet, some of you do, go ahead and put your address here. We're going to put you in a group with access to different telescopes, and we'll give you some more time. And one of my staff programmers, Vladimir, is in the back of the room, and he's grabbing these email addresses and setting up accounts for you, just like we do with the students. And so check your email. You will be receiving, I'll slide down here, but just, put your email address under that list there. You'll be receiving an email like this. Is what the students receive. We can set up collaborations and groups and users in Skynet. So often groups become classrooms, and the users are the students, and they receive an email like this. The only difference is there will be a special code just for you. Once you get this email, it may be in your spam folder, so look around for it. And Vladimir, once you get them all in, shout out so that everyone knows. It's already set up, so you're going to go to this link here that says register. You fill in your name, your email. I think you have to create a password and type it in again, pretty standard stuff, and you'll have access to our network of telescopes. Again, I encourage you to go to some of the other talks so you know what to do with the optical telescopes. I'm going to show you what to do with the unique radio resources today. And it will come with, if I didn't mention it already, 30 minutes of observing time. And that is time on sky. And it's not slewing time, that's not waiting up and you have to hit a certain, it's queue schedule. So you put in your requests, and only the time that is actually integrating light is charged against you. Okay, and keep this page up, because I put like crib notes for everything we're going to do on this page, and we'll refer to it a couple times. There are links here as well, so keep that available to you. Okay, while that's going on, I'm going to go back to the PowerPoint and blather a little bit, giving Vladimir some time to set up the accounts for you. So I'm going to first tell you a little bit about our telescopes. I won't spend too much time on the optical. Again, come to the Opus talk tomorrow or some of the others. But is
that here?
Yeah, it's in one of these two. All 5 of our workshops will be in one of these 2 rooms. I'm not yet sure. They may all be in this one, but I'm not yet sure. Our primary site is Lolo Inter-American Observatory, which is one of the great observatories of the planet. We have a bunch of optical telescopes there. We now, despite this figure, we have 3 sites in Australia. 2 of them are just coming to life right now, but 3 sites. So our best coverage is actually in the Southern Hemisphere. We do have Martin ran a site for a while for us up north, and this picture is from his site. His telescope's been relocated to Saskatoon. It's about to be relocated to Mount Lemmon in Arizona. We've been just wheeling and dealing, trading. So your telescope's making the rounds. And it came from Chile originally. So we'll have some US Southwest access as well. These are the prompt telescopes. These are telescopes that UNC has spearheaded, raised the money for, maintained. They're generally the best scopes on the system. I'll tell you more about them in some other workshop. Then we have our partner telescopes. If any of you have a remotely controlled telescope, it's really only as long as you have the right software in place, and we have lots of different ways to configure it. You can connect to Skynet, become a member of the Skynet network, and use our queue scheduling system. If you have a weather station and all that, it will open the dome for you, close it, and people all around the world will use your telescopes, and it makes it easier for your students to use the telescopes as well. And this figure is a little out of date, but we have a bunch of these partner telescopes. And then what we're here for today is the radio telescopes. So this is the 20-meter diameter radio telescope at Green Bank Observatory in West Virginia. It's 6 stories tall, 20 meters across, so 150 tons. Looks big, but it's small for a radio telescope. I raised about $500,000 for it to be refurbished after the Great Recession. So we have about 10% access to this for all time. And so we kind of shoehorn this telescope in our optical system, and that's what we'll be using today. But my programming staff has had a big effort underway for the past 2 years, really, to unveil Skynet 2, which is really designed for optical and radio on an even parity using modern interface, angular type interface and backend structures that will be rolled out within a year. But coming up, as part of this DoD award, We have brought in University of Tasmania as a partner, and these are the 3 telescopes they're contributing. On the left, we have the Seduna 30 meter, and then we have the Hobart 26. In the lower right is the Hobart 14. I think we have about 3.5% on the 2 larger telescopes, but about 50% on the smaller telescope that's being refurbished, part of the funding. Also, part of this grant, we have some telescopes at Perry Observatory in North Carolina, 2 of them guaranteed, possibly 4. The Arecibo 12 meter, their educational telescope, and there are others who have expressed interest as well once we get this off the ground. I'm really excited about this because for the first time, students will have access to the invisible universe. They don't have to travel to remote locations, and it can be built into classes, as I'll show. Just a little bit about our mission at Skynet. We're 50% research, 50% education. These days, I'm more passionate about the education side, but we're very research active. Once every 20 days, someone somewhere is publishing Skynet collected data. Been in Nature and Science many times. We're the leading tracker of NEOs in the Southern Hemisphere. But on the education public engagement side, we've been a part or have led 4 large multi-million-dollar programs. NSF really wants to see Opus become a national curriculum. DoD is very excited about the follow-up that we're designing. And just from those programs that I know of, I can count 45,000 students. But there are lots of institutions that acquire time on Skynet. You can buy time on Skynet, or you can put a telescope on Skynet. They're doing all sorts of things with their students that I haven't been able to keep track of. So the number is certainly larger than that. Just a bit about Opus and MWU, and then we'll start doing activities. Opus, our place in space. As I said, 24 institutions, 3,500 students. It's doubled in the past year and a half, so we're on a nice exponential trajectory. There is money from the NSF grant for instructors who are interested in adopting this at their institution. And the money is for training and to provide feedback to us, but mostly to carry out surveys and to host a site visit for my education research postdoc, not to evaluate you, but everyone's implementation of these materials is different. We're carrying out the largest study of robotic telescopes at the undergrad level ever. And since everyone has their own implementation, we send someone around, and she's super friendly.
Is that in the US?
US, Canada, funded. Yeah, the funding is Canada as well. Daryl Jansen at University of Saskatchewan is a big player. Yeah, there's funding as well, even though it's DoD money. they don't seem to care about that. NSF cares more about that. DoD is happy with the partnership. Again, these are survey level undergrads, so most of these will not become astronomy majors, but hopefully we can excite them enough to come back and take more courses, either in astronomy or otherwise. And the focus of this sequence, and I won't spend time on it today, is by the title, Our Place in the Universe. A lot of introductory astronomy curricula can be organized around us learning our place in the universe. You can see some of the things that we do there. The backbone of such a curriculum is the cosmic distance ladder. You come to the Opus workshop and you'll see that we measure parallax to main belt asteroids using Skynet telescopes on opposite sides of the Earth. We observe outliers. Well, 7 of these 9 experiences involve the collection and processing of Skynet data. We do a little bit of radio here. We do a rotation curve of the Milky Way as well. But here we're to learn about MWU, astrophotography of the multi-wavelength universe. Astrophotography is the hook. It's not the prime focus, but boy, they get excited about making color images. There's up to $9,000 for participating educators, and here they're playing a larger role. They're contributing significantly to the development of the curriculum, as well as implementation and surveys at their institutions. It's primarily for undergrads who have completed Opus. It doesn't have to be completely Opus graduates, but basically you have to offer Opus once. Once you do that, you can join this group and help to develop MWU. There will be, in the end, 13 modules, and both with Opus and MWU, it's pick and choose. You don't have to do as I say. You can figure out what works best for you and implement it. But in MWU, they're giving 13. It's a split between optical and radio. The theme is color, interpretation of color. So many ways you can interpret color to get physics. In solar system, stars, and galaxies, there's also a big emphasis on light emitting processes, both narrowband processes like H-alpha, H1 in the radio, and continuum processes like synchrotron, Bremsstrahlung, thermal. Here's just an example at the bottom. This was actually an APOD. That's a picture of Centaurus A taken with one of our telescopes in the southern hemisphere, and then the 20-meter radio telescope. Centaurus A does have big radio outflows. And you see, even with a single dish telescope, we can barely resolve, but the jet is oriented as depicted there. Okay, that's it for the spiel. Vladimir, is everyone all good? Okay, so everyone open up these websites, have them ready. The first one is skynet.unc.edu. And I'll actually copy these and put them in the chat for our online folks. Try to. Okay, that is scheduling on Skynet. This one is a collection of independent tools that go with the Opus and MWU activities. We make use of some of them today. They're pretty nifty. Some are downright extraordinary. You should all go to the HR diagram workshop later in the week. And that can be used outside of Skynet as well. And then Afterglow. This is the big image it's online web-based image processing software. It's probably the ultimate replacement for Astro Image J. And the last one is the registration page, which you already have open. Okay, everyone good? No, I will wait a moment. If you all...
Where did you get me in?
Might have your old account.
Just use my old account.
Yeah.
Okay.
Yeah, and there's password recovery if you don't remember it. Okay, our first activity, I'm going to bring up the, oh, wait a second. You got the 3 web addresses out there. Everyone got the 3 web addresses? People online, you good? If not, speak now. Okay. Let me pull up our little cheat sheet here. Close down the chat. Okay, first up is timing. We're going to learn how to observe pulsars with Skynet, and then we'll analyze some data that's already come back. And data may come back if the telescope's not in use right now. Data may come back as we're working. Notice here there's a guide. We've developed a lot of guides. They'll eventually be put in a fancier press book format, but right now they're just Google documents. But you can refer to these guides and work through these, in your own time as well. So all the guides we've developed related to radio are here. But let's pick a pulsar. You can all pick your own. Kind of the standard is 0329 + 54. It's super bright, super easy. You can see the difficulty level. Sometimes the pulsars turn off for a while. So the more difficult it is, isn't necessarily a statement about it being faint. It's just, is it pulsing now or is it kind of quiescent? Pick one. And then go to Skynet. And I'll show you how to carry out this observation. Gotta move the folks over there on my screen. Okay. So here we are at Skynet. And maybe in some of the other workshops, I'll give you more of a tour. You can see all of our Skynet sites, and each one has information about the sites. We have a nifty page called Skynet Live, where you can see what's connected and where the weather's good. We're going to be using the Green Bank 20-meter sitting idle. So the first person get their observation in, will get their data first. And then we have My Observatory. So we're going to go to My Observatory and go down optical and then radio observing. In Skynet 2, these things are become more of an integrated concept. We go to radio observing. And if you're new, or if you haven't used the radioscopes, this page will be blank. Here you can see my previous observations. I have pages and pages of them. But yours will probably be blank. Okay, so the first thing we want to do is go to Add New Observation. If at any point I'm going too fast, just speak up. Or if you have questions, speak up. This is meant to be very informal. So add new observation. And there are a couple ways you can do it. You can find your target on here and click on it. The Skynet 2 version of this is a little planetarium program to help you explore the sky. The Skynet 2 version of this is almost like a recreation of Stellarium. It's about halfway to Stellarium. I'm very excited about the rollout of Skynet 2. But the easiest thing is just type in your pulsar here. Start with PSR, and I'll do 0329 plus 54, and you search on it. You see it found it right there. I'm going to hit the now button. Yeah, now it's pretty high in the sky. This should be very easy to observe right now. If you want to do a different pulsar, totally fine as well. And we've given you some extra time so you can come back after the workshop and observe other pulsars. When it does that, it enters the coordinates here. The name, it's a 1950 coordinate name on the pulsar, but it puts the modern J2000 coordinates here. It gives you a name. You can change the name if you want, whatever you want. Min sun separation. You should probably have defaults of 10 and 20 here. They're fine. Nice thing about radio is you can do it during the day, but you still want to be a little bit away from the sun so that if your target's within 10 degrees of the sun, it will hold it. And you want to be about 20 degrees above the horizon because the horizon makes radio noise. And you come down, you see a little air mass chart. This, the one I selected anyway, is very observable right now. So I'm going to save and continue. Everyone there? On the receiver page. Okay. So as I said, this should have been the 5th of the 5 workshops. And you, had you done the optical workshops first, you would have been now taken to your filter page and select your filter. Here you're going to select, you're going to configure the receiver. It's kind of, it's the analogous operation. The back of these telescopes, they're giant satellite dishes. We have a receiver at the top. And the default configuration is pretty much what we want for pulsars. Low resolution mode. And we're going to use the H1 filter. This is just a 80 megahertz band around 1395 megahertz. That's fairly well protected in terms of interference. And we do not want pulsar mode. Okay, I know that's counterintuitive. There is a pulsar mode, which is super fancy. It does all sorts of things, but it's a total black box. And for education, it's maybe not that great for that reason. So the pulsars on that list were all slow. And so you don't have to do a dispersion measure correction. As that pulsar light, radio waves, I call it light, it's all light, it's radio light, coming at us, it scatters through the interstellar medium. And the faster pulsars, you have to correct for the dispersion measure. And we decided for the pedagogy of this, we didn't really want to focus on that aspect of pulsars. That's more study the interstellar medium. So the students doing this activity are doing bright, slow pulsars, and we're not going to use the pulsar mode. We're going to just collect the data and use our tool and go through the steps ourselves so we better understand period folding and things like that. So no pulsar mode. Save and continue. You can do pulsar mode later and you'll see the automated Presto data product. If you have multiple time accounts, pick one. And so we're now on the next page, and basically everything on that page left at the default. Path type. We're going to change that to track. Radio telescopes are 1 pixel cameras. That's what you have to think about. So here we're going to take our telescope and just point it at the pulsar. We're going to track it on the sky. So path type track. Let's do a 3-minute for these pulsars. 3 minutes should be fine. This is in seconds. So input 180 seconds. You can go longer and get, a stronger detection. But for right now, 180 seconds is fine. The integration time. Oh, the integration time we also have to change. The fastest this telescope goes is 0.021 seconds. We want to sample as quickly as possible because these things are pulsing on a rapid time scale. We're working on it so they can get down to 1,000th of a second, but that's turned off at the moment. So 0.021 seconds. All good? Ready? Okay. Save and continue. Takes you to a checkout screen. Submit. and then it shows ready. Now I'm going to go to Skynet Live, and it should take one of these. It usually takes about 30 seconds to register. There it is. You got mine first. I pressed the button first, so the mount is initializing. And a fun thing you can do with the radio telescopes, if I go to the telescope site page, go down to Green Bank Observatory, because it's our only radio telescope at the moment, and click on Green Bank 20 meter. We have a nifty little interface where you can see the telescope moving in real time. In fact, I can zoom in here. It's I'm going to zoom it out because it's actually up here. It looks like it's taking a long path, but it's an Alt-Az telescope. And so it's actually going the most natural path it can to the source. I want to put webcams on these radio telescopes so we can see these giant structures moving. Students would get so excited, but webcams make radio noise. So,
So what did you click on in this page to see? Green Bank 20?
yeah, so I go to telescope sites.
Yeah.
Green Bank Observatory, then the telescope Green Bank 20, right here.
Oh, okay.
Some sites have multiple scopes, and this one has one.
Yeah.
The formatting issues will improve with Skynet 2. It'll be a totally different web framework. But here you're going to learn the functionality. So it's pretty much gotten in position. I'm going to zoom in here. And this one's not very exciting to watch. It's just going to sit there. But we do have a live feed down here. Right now, just reset the receiver. And it's collecting its data. And we don't see much here, but after 3 minutes, we'll have something to see. But we're not going to wait for that. Your data will come back and you can process it after the fact. I'm going to show you how to process it now using archival data. So if we go back to our sign-up sheet, here's that table where you selected your pulsar. And here, just reminders of the settings I did, so, you know, because you're like, how am I going to remember all this? I have little crib notes here. And of course, there's the guide. The link to the guide explains everything in detail. But I grabbed two good ones, 0329, which is too easy. So I'm going to do the other. You're welcome to do either one. But when the data comes back, it directs you to a page like this. So I'm going to do PSR 2021 plus 5. These are Green Bank's data products. Skynet 2, we will be so Green Bank makes these preliminary data products. Skynet 2 will be making our own. That should be a little bit more robust. Sometimes these don't appear and you have to reobserve. Any of the things we put in today, if it comes back looking not quite right, just resubmit it. But here's one. You can actually see the pulsars, the pulsing here. These little blips that look like noise is the pulsing. There's a calibration observation at the beginning and the end. There's a little radio noisemaker up next to the receiver of all these radio telescopes. It sends a set signal through, so you can test the system and see how it's performing. You also get a spectrum here. I noticed some RFI at 1400, and this is the hydrogen, neutral hydrogen emission line at 1420. Anyway, we're going to go up here to continuum, calibrated, and just grab that data. You can look at it if you want, but right-click, save as, download it onto your computer. In Skynet 2, see with the optical, you don't have to do this. The optical data appears immediately in the analysis platform, Afterglow. The radio data, as it was hacked in, we have to kind of download and upload. In Skynet 2, you'll see less of this. So I downloaded it. Now we're going to go to that other page you brought up, the graphing tools. I don't think I brought mine up, so I'm going to bring it up now. Page that looked like this. So come here, and you can see there are a whole collection of tools for Opus and MWU. Cluster Pro Plus is something else. I encourage you to go to that workshop. But let's go to Pulsar. This is one of my educator group and my programmers. Actually, undergrad programmers did most of this here. Did over the past year or so. And I'm going to get rid of my download bar so I can see the whole thing and just upload that file that you just downloaded. Here it is. Give it a second to come in. Okay, and so here's 3 minutes of data on Pulsar 2021 plus 5.1, I think it was. You can zoom in, you can see individual pulses. Sometimes you can't, but that's why we're going to do I was going to say Fourier analysis. It's like a Fourier analysis. Fourier transforms require evenly spaced data, and these are not perfectly evenly spaced, so we use Lom-Scargill. But before we do that, I also can point out we have a place you can input titles and axis labels, but you get it. X is time, Y is intensity, but students can enter this stuff and save their graph. It actually makes them sign their name, and we put it in the EXIF data. So you can check, you can do, if you put an EXIF view in your browser, you do a one-click cheating check to make sure that it's actually theirs that they turned in. But a fun thing to do, I'm just going to sonify. I'm going to turn my sound on for a second. No, I'm not. How about one of you sonify? Oh man, I'll turn it on, but I won't say anything. Let's see if this works. No, I'm sorry. There it is. There it is.
Could be.
Yeah. Oh, I didn't need to turn my sound on. It's being piped through. A little noisy, but you can hear the pulses. But again, not the case in every pulsar. Sometimes this is just noise at this point. I'm going to stop it. Okay. And somewhere, if I zoom in here, I can get a crude measure of the period. It's about half a second for this pulsar. So, yeah, go. Your question?
No, just clearing my throat, sorry.
Okay. And the students actually love the sonograms. There are many things they liked in the MWU course, but the sonograms was a little pleasant surprise. So now go to the periodogram page, compute, and it's going to compute a Lom-Scargill periodogram. Takes a moment. The more data you have, the tougher it is, and you'll get some hits. And just the brightest one is not necessarily the correct one. It could be a sampling issue. We're only doing 1,000 points, and this pulsation was measured so well, it's very narrowly defined. We might be missing the peak. That's why I checked real quick. It's around half a second. This is the period. Here's 0.25 seconds. No, it's not. 0.25. Oh, this is 0.25. This is actually the overtone. This is the primary period. That's the overtone. If I zoom in, let me do like 0.4 to 0.6. Really focus on that primary pulsation there. You can see it there with a little bit more definition. I can keep zooming in if I want, but it has a period of about 0.5291. You can also go into a frequency mode. I'll do that just once here. And you can see overtones, and there's something else as well pulsating here. Anyway, let's go to period folding, and you input that period 0.5291, I think I said it was, and so there we go. It's currently showing 2 periods, as often standard in period folding. It's sensitive to that 4th decimal place, so you may want to tweak it up. There's 0, 1, 2 is even better, 3 is lower. So 0.5292, and they can do a number of things here. First, I'll sonify it. Should sound a lot cleaner. There's some thing with the audio before that I had to trick it to broadcast in the room.
Oh, you might have to share screen again and then put like share sound.
Oh, okay. Am I not?
There's like a separate box you have to click when you share.
Okay. Yeah. That's right. That's right. Yeah, I'm going to stop share. I'm going to reshare. And I'm going to click the
Yeah.
share sound. There we go. Just clean signature there. But there are other lessons. It's not just, okay, we got pulses. We show the difference here. Now there's a calibration issue. You have to calibrate the there are 2 channels, 2 orthogonal channels on every radio telescope. You have to calibrate. You do that by looking at a non-polarized thing. The calibration is about 1.25, but actually it doesn't matter what you put the calibration is. See, they do not cancel out. And that's telling you this signature is polarized. And think about it, as the neutron star is sweeping across, the field lines come out and they're curved. So when this one points towards you, it's curved this way. And then on the back side of the pulse, it's curved that way. So you get a polarization difference. In this way, the students learn this is non-thermal emission, introduces them to lessons in synchrotron and curvature radiation. The other thing they do is they take the pulsation and they compute the maximum size of the neutron star. And from the ones they're observing, these are slow pulsars, they can say neutron stars have to be smaller than about the size of the Earth. But then we give them some faster ones. And let me just load up a couple of these for fun. These are archival, pre-folded. I forget which is which. Let's try this one first. This one's a little, yeah, this one's fast. That might have been the fastest one. Yep. I'll load up another here. Anyway, they go through these, eventually get to the fastest known pulsar, which spins 700 times per second, and they update their constraint, and they get something very close to the size of a neutron star because it's rotating almost at the speed of light at the equator. Okay, so that's an example of timing, something you can do the survey level. There are questions. Let's move on to spectroscopy. Okay, spectroscopy. Again, let's go to our little cheat sheet and we're going to pick a target. Is it this? Nope. Here it is. So sliding on down. Okay, spectroscopy. In the OPUS curriculum, there is a little bit of introduction to spectroscopy. They take H1, cold neutral hydrogen spectra at 12 locations along the plane of the galaxy and do a rotation curve, and then can measure the mass of the Milky Way. We can throw in the LMC and SMC with some information that they can't measure, but it's a sampling of dark matter. Here in the second curriculum, doing a number of things. This is near the end of the curriculum. They're moving on to galaxies. There's a guide here. This spectral stuff's in the second half of the guide. And so here's some nearby edge-on spiral galaxies. And again, the difficulty level is here. So pick one. Give you a second to pick one. Then we're going to go back to Skynet, and I'll show you how to observe one of these. Then we'll look at some data I've already collected. Okay, so back to Skynet. Get rid of that. Here's Skynet. Again, radio observing. Add a new observation. And then enter your object. I'm going to do sculptor, but it has to be the NGC number that was provided in the table. This is NGC 253, edge on spiral. I'll show you a picture of it later. Down here in the southern hemisphere, but not so far south that we can't see it. In fact, it's actually visible right now. And so the same values here are fine, 10 degrees from the sun, 20 degrees above the horizon. And save and continue. The difference here is we're going to study the H1 line, measure Doppler shifts. And so we don't want low resolution mode, we want high resolution mode. And we want it really centered around the H1 line. You can use these defaults. I like to change, it'll be in this, so in high resolution mode, you get two spectra, each are much smaller, only 15 megahertz across. And you want the H1 line to land in one of them. You can use these defaults for that. That's, well, some of them are redshifted. So I tell my students to change the upper one to 1419, and the other one has to be 15.625 away. So 1403.357. Okay, so 1403.357 would be a spectrum, but not including the line. 1419, the line will be in there. But high resolution mode, that's the key thing. Save and continue. Again, slow me down if I'm going too fast. You pick a time account. And this time we're not going to track. You can track, but the cold neutral hydrogen from this distant galaxy will be lost among much larger instrumental effects. So what we do is an on-off spectrum. So select on-off, and for these about 300 seconds is good. It'll do 300 seconds on target Then under right ascension or declination, I normally do right ascension, I put in a 2-degree offset. It'll shift over 2 degrees. The beam, the blurring scale of these radio telescopes at this wavelength is 3/4 of a degree. Always keep that in mind in the radio. But this is a couple beams over, and then it will subtract the 2. And the rest is fine as is. So you can save it and then deploy it. I'll check Skynet Live here. It's probably still doing, yeah, it's doing Martin's pulsar right now. But eventually it'll get to the point, let's see, something else is coming up. See what's coming up next. Possibly another pulsar, but maybe it's going to start the on-offs. Takes a while to think. I'm not going to wait for it. We'll just go straight to the archival data. Even though I'm here waiting for it, but it will pop in. There it is. It's me. I was first. So I guess we're done with the pulsars. Now we're going to do the on-offs, and I was first. Okay, so let's go back to our sheet here. Again, there are the crib notes, and then I have a few examples here. And there's no fancy analysis we need to do. Let's just take a look at some of them. I just did Sculptor, and what will come back will look exactly like this. Again, these are the Green Bank preliminary products. We'll be developing our own once we have many radio telescopes. There'll be a uniform framework for this, but you can see it here. So it's an on-off spectrum. Let me show you the, move the zoom controls. Here's an on spectrum. And you can barely see there's something going on here. And that's Milky Way hydrogen. The off spectrum is similar, but if you subtract the 2, actually, let me go back to the on or the off. You see the wiggles. Those undulations are not physical, it's instrumental response. But by going on source and then off source and subtracting, you get rid of most of the instrumental response. You may cancel out a lot of the Milky Way hydrogen. And so you're left with the classic Tully-Fisher horn-shaped profile here. This dip right here is incomplete cancellation of Milky Way hydrogen. But from here to here, there's actually a live spectrum option. I'll pull it up. And you can come down here, grab the magnifying glass, make a box. You can see it here in both channels. So from this, you can get things like from the center, that's the line of sight velocity. And for a lot of these, if you have them look up the distance, take the ratio, you have Hubble's constant. Unless it's a Virgo cluster member with some extra velocity, these give usually pretty good Hubble's constants. The final lab of Opus is being redesigned, and they're going to get their redshifts this way. And their distances from a Cepheid or a type 1A that we give them in the source. And then from center to edge, that's the rotation speed. You combine this with some knowledge of the size. Maybe they take an optical picture, and knowing the distance, they can measure the angular radius, get the physical radius, and they can calculate the mass. They can weigh a galaxy in this way. And there are other ones we can look at, but I'm going to move on in the interest of time. We have till noon, right?
Mm-hmm.
Okay, I think we're doing fine. Questions on that? We did timing, we did spectroscopy. So
your NGC 253 shows up as very low to do any observations now.
it was low in the sky. I just, it is high enough. You can lower that minimum elevation from 20 down to 15 or even 10, and it still works. You may pick up some background radiation, but it's going to be broadband, so it's not going to affect the line. And very soon I'm going to have telescopes both hemispheres. So, but you can get it. You may have to wait for the right time of day, of course. And these radio telescopes, they point all the way over to 0. So it's not like you're limited. It must be above 20. It must be above whatever. They point all the way over. As long as you don't have a physical obstruction, you can go pretty far south. Most radio telescopes do. Okay, now mapping. And I mentioned that we produced some fancy algorithms. Here's a link to a 50-page AppJ sup based on new fancy statistical outlier rejection techniques that we also developed. That was a 50-page AppJ sup. Here's a guide for making these radio maps, and there'll be more in the afternoon. May is running a session on optical and radio in the solar system. But pick one of these bright sources. I'm going to show you how to make a map. SIG A, Cass A, Tau A, Orion A, Virgo A, or the moon. These are the 6 brightest things in the northern hemisphere. Fornax A is actually about as bright as Virgo A. You can do that as well if you want. You pick it, and while you're picking, I'm going to show you a little bit about the algorithm here and how it works with the single dish telescope. Okay, so again, these are 1 pixel cameras. So if you want to make a picture, you have to or move the telescope across the sky. There are different patterns. Sometimes we use daisy patterns. They have certain advantages. The standard pattern is a mapping pattern. And we have algorithms that will then plot this data up and fill in the gaps. Come back to that in a second. This is what we call a raw map. You can see the map was made in a left-right direction. You can see the streaking. This is just noise fluctuations. The noise is not random, it's pink noise. It's somewhere between a random walk and random noise. And so you see little streaks that develop left, right. Here is some interference that happened during one of the streaks, went right through. That's quasar 3C273, the first thing with the redshift. That's Virgo A, the center of the Virgo cluster. And here we got too close to the ground. Okay. The algorithm does many things and it makes it real easy. Students, just by pressing a few knobs, they can do this. It goes through a background subtraction algorithm. It goes through an RFI cleaning algorithm. And since the data is not actually on like a CCD, we can plot it in different coordinate systems. There's a galactic coordinate system with the same data using a projection in an equal area projection, which helps with photometry. And just to show you some of the cool things it can do, this was done on a lesser telescope. The previous slide was the 20 meter. This is the Green Bank 40 foot, which is a teaching and training telescope. I've used it since 91. I love the thing, but it's not cool. 20 meters closed loop liquid helium. This is just fans, okay? So this is not a powerful telescope. It was great for testing the algorithm. Here are 2 maps of Andromeda taken 2 days apart. Here's one, here's the other. You're like, oh crap, can't see anything. But after background subtraction, here it is, and then here's the combined and RFI clean. So the algorithm is really powerful at pulling stuff out of the noise. Here's another example of the RFI cleaning. Of course, if you can identify the frequency, you can remove it. But that aside, here's a map. It's an up-down map. And the Roanoke Airport transmitter was beeping once a second. So as we're going up and down, it's going beep, 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 and just filling it with all that junk. But the structure is smaller than the beam pattern in the telescope. So we have fancy spatial filtering. Once you filter it all out, you get this, and it's polarized. The other channel doesn't pick it up. So here's the other channel. So you can see how well, even with this extreme interference from civilization, we can recover the astronomical underlying data. It's a very powerful algorithm. Here it is. This is a higher frequency. This is X band. What I've been showing you so far is L band, 1.4 gigahertz. This is 9 gigahertz, higher frequency, better resolution. And we're going to have a lot of telescopes with X band integrated into the system a year from now. And you can, this was the great eclipse. You can see the moon passing over the sun, and you can see sunspot groups. They stand out. Even the moon is emitting in the radio. We learn more about that this afternoon. Yeah, I'll come back to that. Let's make a map. Let me show you how to do that. Again, it's a powerful concept because students can relate to, you turn into a picture, then they can start doing optical tasks. I'll go to Skynet. That was not Skynet. This one's Skynet. Okay, radio observing. Gonna add a new observation. If I want something new, something quickly, let's see, here's Cass A right there. I'll go after Cass A. Now, if you want Orion A, you actually have to click on it on the map. The Sinbad coordinates of Orion A are off. So if you want Orion A, here it is. Come over here, zoom in, and click on the orange square. Otherwise, it will center over here. But I'm going to do Casa. I searched, I found it. It's been marked. There it is. It's filled in the coordinates, 10 and 20. Air mass is good. Save and continue. Here we're going to go back to low resolution mode. I'll show you an example of a high resolution map in a second, but this would be a low resolution map, brings in more signal to noise. So an 80 megahertz band around 1395, not in pulsar mode or anything like that. And save and continue. We've chosen our frequency range. And then we're going to make a map. This is a little bit more involved. With an optical camera, you have a CCD, it's fixed size, but we get to pick the size of the field of view. We get to pick the spacing of the points. So you get to decide how many pixels across your CCD is, or CMOS, and the size of the pixels, essentially. And you can do in degrees or beams. If you're just going over a source, I recommend beam widths, and 7 beams by 7 beams is pretty safe. The 1 sigma, the full width of half max of the source is 1 beam. 3 beams covers the source, and then you want some background as well. So let's do a 7 beam by 7 beam map. It won't eat up a lot of your credits. You can raster in right ascension, you can raster in declination, doesn't matter, whichever you want. And you have to sample frequently enough. And I normally do 1/5 beam rasters. As long as you're sampling at 0.4 beams, that's Nyquist. You're getting all the information you need to reconstruct that Gaussian shape. But the path of the telescope is never perfect. Wind blows on the telescope, it's doing these rapid turnarounds. And so I like to do a tighter map, get extra information. And I click this box, same as gap between. And so it's going to be 1/5 of a beam going along the sweeps and 1/5 of a beam from sweep to sweep to sweep. So a grid, but it's not going to be a perfect grid because the telescope's moving. This is called on the fly observing. It'd be terrible wear and tear in the gears to point, stop, collect, point, stop, collect. So the thing's just going to move, and we're going to collect the data as it's moving. Down here is how long you want to integrate at each point, which is really the integration between one sampling and the next. It's tied to the slew speed. You can integrate 0.5 seconds, and I just slow down the telescope because now it takes longer to go from point to point. So you can pick slew speed or integration time. Just keep it. I'll go back to 0.3 here, 1/2 degree speed. Keep it under a degree. Once you get above a degree, the pattern starts to break apart. It can't move. It can move that fast, just not very reliably. So we've designed our field of view, our sampling size, save and continue. We're going to submit. Okay, and so those on-offs take a while. In fact, my first one's not even done, but maybe at the end of the talk, if there's time, we'll come back and see any rasters executing. These are fun to watch on that live page because you can see the telescope carry out its pattern. Eventually, I'm going to get webcams, but I'm going to put them behind Faraday cages so the observatories will accept them. And I think the kids will just be blown away watching these 6-story structures move because they pressed a few buttons half a world away. Okay, so you're now collecting a map. While that's proceeding, let's analyze a map. Everyone still with me? Anyone not? Online, shout out if I'm losing you. It's tough with online people because they're often on one screen. It's hard to watch me and do the things unless you have a double screen. So again, there's a guide for how to do this, and there are the crib notes of what we just did. Come down here, let's grab this one. This is Virgo A. I took it a while ago. 5th brightest thing in the sky, I think, in L-band. And this is the results page. I haven't taken you here yet, but once your observation's done, if you go back to Radio Observing, you'll see the results, and you can click on them, and it takes you here. And the first link is Greenbank's data products. The second link is something we just recently hacked in. This is the Radio Cartographer Skynet suite of algorithms. Really built for Skynet 2, but I couldn't wait. So it's hacked in here. It's going to be nicer in Skynet 2, but it's functional, and I'll show you how it works. But first, let's take a look at what preliminary data products might look like. This was exactly that, a raster. I think this was 6 beams by 6 beams instead of 7 by 7, a little tighter. And you see it's going back and forth, back and forth. The background levels are changing as it goes back and forth.
Sorry, how did you get to this page from the previous page?
Yes, right at the top, there's a link provided by Greenbank.
Yeah.
Yep, go there. Again, this will be generalized in Skynet too. But you can see as it's going back and forth, it suddenly passes over, gets a little blip. It comes in a little blip and stronger and weaker and weaker. And this is as it's going over the source. Here you see some RFI at the end. If we look at the integrated spectrum, 1381 is a common frequency for radio frequency interference. But I'll show you how to cut that out and just magically, you can leave it in. The Skynet algorithm with its spatial filtering will take it out. Excuse me. But it's better just cut it out in frequency. It's not even there. Also, here's 1420 cold hydrogen. If we slide down, you can see the path that was actually executed, not a perfect raster, but there's enough data spread out that we can reconstruct it. And then you have Greenbank's reconstructions, and they're not doing anything fancy, no background subtraction, no RFI removal. In fact, the computer that measures the fluxes and the computer that measures the positions, their times get off. And that's what you're seeing here, the split, because it's thinking the flux is at a different position. But built into our algorithm, we fix that. We do autocorrelation integration between the sweeps. Students don't even, it's a magic button and it just fixes it, as you will now see. So we're not going to rely on these preliminary data products. We're going to make our own. Let's come over here to the this page and go down here and hit create a new job. The buttons are not quite in the right place. Again, this was a hack we put in just a few months ago because we offered MWU for the first time to students to try these things out. And put in your name so you can keep track of whose is who. And I don't have to go through all the details. Both maps look good, so I'll sum the 2 channels. I'm going to keep it in RA deck. Time delay should be set to auto, and that's it trying to piece those sweeps back together. We're going to let it measure what the time delay was between those 2 clocks. I like to include the raw image, it slows down the processing, but this processing only takes about 30 seconds. And then you can see where you went from to where you went to. Frequency range, we're going to use the full range for this particular setup. We were observing from 1355 to 1435, but these are common skip frequencies. We have the interference at 1381, so you may want to add a skip frequency from 1380 to 1382. I didn't actually see any interference there. I'll take that one out. And you may want to skip or leave in. If you want to see the cold hydrogen, leave it in. That's fine. 1319 to 1321 will remove the cold hydrogen. Maybe I'll leave it in just to see what it looks like. Lastly, down here, these are the knobs and levers. Background subtraction scale, 6 is a good default for sources. RFI subtraction scale, really all these things, you have some choices. Am I looking at a faint target or a bright target? Bright targets will have area rings and reconstructing this image, filling in the gaps is a little different if there's that kind of oscillation. All you really have to do is hit bright target. There's obviously other controls for finer, more subtle things that you may want to do, but this was pretty easy. You put in your name, any skip frequencies that you wanted, bright target, let's go. This was programmed by one of my undergrad programmers. He has 3 emotional states. When he's excited, he says, ooh, no, that's surprise. Excited is let's go. Yeah, he's excited, he's like, let's go. And surprise is ooh, and disappointment is boo. And so that's why it's the let's go button. Okay, it's pending. You can see other ones I did before, but if I refresh, completed. It didn't take long to do that small of a map. If you do a big map, he may be waiting a little bit longer. And we got multiple people here. So then click on yours and it'll reload your settings and you can download it. Otherwise, it would just download the most recent. All 3 should be the same if you all press the same buttons. And it's downloaded. So let's go to a new program for you. This was the other link, the Afterglow link. I'm bringing up the dev site, but you brought up the main site. It doesn't matter. This is pretty fancy stuff. This is the thing that's going to replace Astro Image J. It's mainly for optical. NSF has put a lot of money in this. Now DoD has as well. Go to the other workshops to learn all of its amazing capabilities. Web-based. The optical data is already there. You don't have to download and upload, but the radio, you still have to do that. So let's get our radio data in here and take a quick look. Then we'll do one more thing. Time permitting. We're great on time. So if you're in Afterglow, is everyone in Afterglow? Okay, you had to log on. You can log on with your Skynet credentials. Since you're already in Skynet, just say Skynet credentials, and then you're in. Okay, let's go to Open File. And let's go to your workspace. You have a couple things. There's a sample directory where we have some sample files. Any optical data you collect yourself will be under Skynet. But let's go to Workspace. And there's an upload button. And you can upload that data that you just downloaded. Super small file. I mean, it's a beam, right? We did 6 beams. Imagine zeroing in on just one star of an optical image and going 6 beams across. Tiny, tiny little patch. So it should load super quick. It'll be somewhere in your directory and then open it back up. Virgo is 3C274. So you open it and we'll load a complicated file with many layers. If you press this button here, zoom to fit, and make it big for you to see. And that's the main image. There are different layers. If you hop down the bottom layer, you can see the original image. This is before time delay correction. I took out the RFI, but I didn't take out the hydrogen. So we've got some hydrogen clouds. The other ones really don't matter that much. The second one is the path map. After it's done the time shift corrections, removed a few points that were RFI contaminated. There are 2 shades there showing you whether it's going left or right, or up or down. The other ones are kind of more technical weight maps to help with the reconstructed surface. That's the other thing I should say. This is really all that's being collected. Points, fluxes at points. We have to fill in the gaps. Most single dish radio algorithms, they'll do a Gaussian blur. But these things are already so blurry because they're radio telescopes. So we actually model. We go to each pixel and build a model around it, fit it weighted towards the center, and then take just the center point, then go 1 pixel over, do it again. So it's pretty intensive numerically, but it does a great job. And so here we have Virgo. Maybe I'll put it on right target. And there are all sorts of other things you can do. You can photometer this just like an optical image. In fact, there's this little blob right next to it. That is M84. It's also a radio galaxy. It just happens to be right there. Virgo's really bright. A lot of things are faint. And if I were to be in a different part of the sky without Virgo right next to me and make a map, this would look very bright and very well put together. It's mixed a little bit. You can see the area ring just slightly going around. And I'm just playing with the brightness and contrast settings that should be off on your right. And you could do things like photometry. I'm not going to show you because you'll see this in the afternoon lecture, where you'll go through some lunar data. You measure the brightness of the moon compared to a calibrator, and then turn that brightness into a temperature using the Rayleigh-Jeans limit of black body. All sorts of physics that you can do. Okay. Everyone good so far?
Sorry, Dan, you said that the data was small. I've got a big FITS file, like 64 megabytes.
Does it look like this when you load it in?
I'm still loading. So I was supposed to get it from Skynet,
Yeah,
download it,
yeah.
but it came out really big.
Strange. So you were in Skynet.
Yeah.
Here it was loaded up. And where are you here?
I'm not seeing it there.
You must have gone to a different link.
Yeah, I just signed in on my own account.
Okay.
That's okay, don't let me.
We'll figure it out.
Yeah,
Yeah, once you make a map, the idea is you go back to radio observing, you find your map, tells you what it was, like here's the cast map that I just did. And then the data, the green bank data hasn't been processed yet, so I don't have it, but yeah, if you're on some other page, I'm not exactly sure what you made a map of, but you may have made a big file, in which case it's slow.
right, okay, thanks.
Okay,
Can I ask, the
Yeah.
image is total intensity? Can you do like polarizations?
yeah, so there are two channels for that map. Let me just go to whatever page I was at for. So for that map, I summed the two channels, and often the sources are close enough to unpolarized. I'm just boosting signal to noise by doing that. But some sources are polarized, and so you can make the left, you can make the right, you can combine them in different ways. Here, at risk of
Sorry.
losing time, I have a great example of that. I have a little radio astrophotography page. And again, thank you for letting me use my own computer because I can find these things real fast. Here, this is the North Polar Spur. It's a big structure. You can see it here, probably a whole bunch of supernovae a long time ago. And here are the two channels colored red and blue. If there's unpolarized, it would be all purple. And here you see variations here. To get actual polarizations, you need more than just two. You have to have some other angles. And there are tricks for doing that. It's an alt-az telescope, so observe it at different times of the day. You get different angles, and you can reconstruct Stokes parameters. Yeah, it's a little bit more advanced than we do with these students, but as you saw with the pulsar exercise, they at least can see polarization is present, and that leads to instruction of non-thermal emission mechanisms. Okay, color. Let me just say a few things, and then we're going to do one last exercise, and then if I have time, I'll show you just a little bit more. Put you all up here. 13 minutes. Okay, color. On the optical side, we use color in all sorts of ways. Color of stars gives you temperature. Hot gas like H alpha, O3, S2, they colorize. Color gives you composition, gives you temperature. You can calculate densities. Color is used in all sorts of ways on the optical side. We try to use it in all sorts of ways on the radio side. I think this is what I want here. This is one way. We're not going to do this today. This is an algorithm we designed called naturalization. It's not commonly used, but imagine this is your frequency range that you observed. And the nice thing about radio is you're collecting a spectrum at every point, whether you want to or not. So you make this map, you actually have 1,024 maps if you want after the fact. And so using that same interface, if we explore it a little bit more, you'll see there are ways to break it down. I want just the first third, the middle third, the second third. So we take the observed band and break it into 3 subbands, and you have red, green, and blue. You have to do a calibration source, or else the relative levels of the bands are nonsensical just due to instrumental response. So you do the same thing for a calibration source, get it all calibrated. And you can make that into a red, green, blue image, but it'd be kind of white. These bands are so close together, the fluxes are about the same, comes out white with maybe a tiny shade of blue or red. So we naturalize. We take this tiny spectral index and extrapolate, and this tiny spectral index and extrapolate and combine the extrapolated red, extrapolated blue, and the original green. And we extrapolate to the spacing that matches that of the human eye. So this is naturalized, and what that means is, what color would this appear if the eye worked at radio wavelengths with the same space and that we have in our eyes with our red, green, blue? And it's something I always wanted to try. And so far, I've done some larger regions. I'm not going to bring them up now, but this is just to show it works. We're still tweaking the algorithm a little bit, but thermal sources have a +2 spectrum in the radio, the Rayleigh-Jeans limit. They should be blue, just like an O-star is blue to the optical. Bremsstrahlung sources are kind of from +2 to 0, depending upon the density and the optical thickness or thinness. And synchrotron sources go from 0 to an inverted spectrum, like -1. So in the optical, stellar colors give you temperature. In the radio, once you do this naturalization, that's the moon. It's a thermal source in the radio. That's Virgo A, which we just did. That's a synchrotron source. Color is telling you emission mechanism. So one of the upcoming modules, we have 3 left to design out of the 13. They'll take a big chunk of the radio sky, map it, make a source catalog, naturalize it, and they can kind of say, oh, that's a supernova remnant or a supermassive black hole because it's red. That is blue, but not thermal blue like an O star, so it's a Bremsstrahlung region. That's blue, it's the moon. It's basically everything out there outside the solar system is Bremsstrahlung or synchrotron. So color teaching emission mechanism, which I think is an awesome, awesome tool. And we're still exploring this one. So I'm going to show you, the last thing I'm going to show you, and we can do it together probably, is we're going to use color a different way to show velocity. Instead of emission mechanism velocity, and this is Doppler color. There we go. So here's just a little on-off spectrum of Andromeda, give you some idea. And it's the center. Andromeda is 4 degrees across. We can resolve Andromeda with our radio telescopes. Most things you can't resolve in the radio. This you can barely resolve. And but this is the spectrum just of the center. You get the center wavelength, but there's actually more light if you look on one edge over here, more light on the other. You can kind of see where it crops off. So Andromeda, just like you saw the Sculptor emission line spanning a range, the Andromeda H1 emission line spans a range. And so I have the students do 5 separate integrations, one from 1420.5 to 1422.9 that gets the whole Andromeda range. In optical parlance, this would be our luminance filter. Optical astrophotographers, they don't just combine red, green, and blue, but they have a luminance, which is a high signal to noise, covers everything. They take the intensity from the luminance and the color from the other layers. Then I have them integrate a small band here, a band here for green, and a band here for blue. And lastly, I have them grab a tiny band right here around the Milky Way hydrogen just to see where it is. Okay, so that's the plan. So in the folder or in the file here, I take you to a map of Andromeda that I did. Now I've already processed these maps, but go ahead and click on this link. And down at the bottom, you can see I labeled them, and forget the second sets, the top 5. H1, that's the Milky Way hydrogen, blue, green, red, luminance. So if you want to do this along with me, click on one, download it. Click on the next one, download it. Download all 5 of them. Give you a second to do this. Green. And later workshops, particularly on the last day, we're doing one on star forming regions. So we're going to get into some serious optical plus near infrared and mid infrared astrophotography. This is just going to be a tiny little taste. So once you download those 5, go ahead and upload them. And I'm going to switch over to regular Afterglow. I think I may have them already uploaded. Let's see. I don't. I'll upload them here. Upload them to your workspace. See if I have them. Oh, I do have them already, so I don't need to upload. Just click on all 5. Load them in. And the students this semester, when we taught this for the first time, they're kind of interested in the radio, but when we did this exercise with them, they got really excited. So once they load in, let's look at the main images. First for luminance. Okay, Andromeda's resolved, right? It's a disk galaxy, edge on. We're seeing it there. Now let's look at the red main. There's one side. That's the side that's redshifted compared to the center. Green was the frequency range was chosen to capture the center of the galaxy. And blue, again, if you need to frame it up, you can zoom to fit down here, the other side of the galaxy. And just for completeness, here's the H1 frame, gas all over the place, because we're looking through our galaxy to see Andromeda. Y'all with me? Okay, let's do the following thing. 5 minutes, this would be perfect. For the mains, right click remove from layer for each, just the main. If you don't see it, you can stretch it out a little bit. It's the first one in the list. Right click, remove from layer. Right click, oops, that's the path. Right click, remove from layer. We're separating these out, and then we're going to group them into their own group. Right click, remove from layer. I think I had save. Let me try again. Rename, okay.
Oh, wait,
Remove
no.
from layer.
Sounds good.
What? Did I do it again?
Yeah.
Oh, yeah, yep, I did it again. Remove from layer, and then the red. Remove from layer. Then grab those 5. Here's the red main, luminance main, H1 main, green main, and the blue main. Click on them all. Then up here under the triple dots, you can group them. Now they're their own group. Okay, it's down here somewhere. Here it is. Okay, we've got to do a little bit of work to turn this into an astrophotography thing. And again, all the workshops are out of order. So if you took the other ones first, those make more sense. You have your color ones on the bottom, and you can slide them. Just drag to slide. Okay, so the color on the bottom, then the luminance. The luminance has to go above the color. It's how luminance filters work. The intensity will be taken from that layer, the color from the ones underneath. H1, put down the top, and now turn it off by just clicking on the eyeball. Turn it off for now. Okay, and going through these, here's the blue one. If you right click, we're going to change its color to blue. On the green one, right click, change its color to green. Red one, right click, change its color to red. And the luminance, we got to do 2 things. Click on it. Change its color to gray. Luminance filters have to be gray. But then one more thing, under blend mode, you change it to luminosity. That's what makes it a luminance filter. We'll come back to H alpha in a second, but if you click on the group, there you go there. And there are games you can play. I'll just show you real quick in the final couple minutes here. If you go to display settings, it's this first tab, and click on the luminance filter. Under here, under color composite, we're going to teach you all the astrophotography in the 5th workshop in much more detail, but just click on link layers. Then you have control over all luminance and color layers from a single place. I like using the mid-tone stretch mode. And I hit default, and then I can change the mid-tone layer to kind of get the shape that I want. 99, you know, that looks pretty good. If I go too high, it kind of disappears. But again, that's a game you can play. Now, lastly, let's turn on the Milky Way hydrogen. And we have to color that as well, something. And I'm going to color it Bomber. In optical astrophotography, you often do an H alpha layer. This is not H alpha, it's H1, but you often do an H alpha layer, and it's colored Bomber color. So I stuck it in here, Bomber color. If I want, I can control it separate. Sorry, I'm using the wrong side of my mouse pad. I'll come up here under display settings and switch to the H1 layer. Now unlink it from the luminance layer. But then I can tweak, like if I lower this mid-tone level of brightness. So here's a picture of us looking out through the Milky Way. You see all the clouds, and then in the distance, you see Andromeda spinning, and you see the spinning in color. And the things they can do from this, from the velocity, from the frequencies and Doppler equation, they can calculate the velocity it's moving towards us. You tell them there's no lateral motion, so which is true. So they can calculate the collision time scale, about 3 billion years. Again, they can also get a rotational speed and mass. And here they can measure the size of the galaxy themselves, at least the angular size. You give them the distance and small angle formula, and they can calculate the mass of Andromeda. This is a nice pairing for the spectroscopic one, which usually follows this. And it's 12. I was going to show you stuff with the Galaxy Capstone where they combine optical and radio. But I think you get the idea. Some radio galaxies may have a bright synchrotron source in the middle, supermassive black hole, active galaxy. Others, like spirals, they have strong H1 signatures, and they can piece together a pretty amazing story of galaxy evolution by doing a handful of things. Al, that's my news feed, I guess. Al, stop there. Thanks. Questions?
So this is, yeah, super impressive. So if I wanted to get it for, let's say, a small upper year class, and we wanted to do some activities, how does that work?
How does it work? Yeah.
Yeah,
So since we're still developing, we're still working on the trick is, we're using a global network of telescopes, and it's not free to run, right?
Yeah.
So the way we've done Opus for all these years, some institutions, their institution supports and they buy telescope time. Most institutions, the students buy a textbook. It's fully online by Cengage Learning, which is the second biggest distributor in the country. And it's $65. And the Opus labs, which are simpler, they're more cookbooky.
yeah,
It's all there in an interactive format. It tells them what to do. They do it, they input the answers back, a lot of auto grading. And the $65 pays also for their telescope time. What we end up doing with MWU is not yet decided, but since a lot of people are mixing Opus and MWU, it may just be, we say buy an Opus account and that covers your telescope time. This is more telescope time heavy. And so the students often work in groups of 4 as
Right.
well. Yeah. But, it's not free. I know there's a big push for that. But, these networks are expensive, and $65 for these kinds of capabilities, it's far less than many textbooks and
Yeah.
far cooler.
and if say a student bought one, about how much time would they get with that 65?
It gives them 30 minutes, and that's for the Opus curriculum. We're still trying to figure out how it will work with MWU. I think we're going to have to get it closer to an hour, and then you share between 4 people. And that should be enough to do the full MWU curriculum. The most people are going to be picking and choosing, and the Opus may be sufficient. For many of the Opus activities, it doesn't require a lot of time. It's the optical astrophotography stuff that breaks the bank. And so that's a little different.
Yeah, I mean, there's some of the stuff I imagine you could do even as a small class, like my classes sometimes have 8 students, 10
Yeah.
students. Could all do it together.
I'll just put up my contact info. So many things here, I can't find the button. Now, they're pretty pictures of galaxy evolution and their stuff, but here's the contact info. There are more links. Those are mostly about Opus, but there's also my contact at the bottom. I didn't have time to talk about the community, but there are almost 30 of us now. And we meet once, twice a week, and it's just wonderful to have, a lot of these astronomers, they're the only astronomer at their institution. This is just a happy, excited community building things. Instead of finding software that doesn't quite do the job, I have teams of programmers building the software to their desires. So it's a fun community to be a part of. I'm over. Thank you for coming.
Well, just one more question.
Oh, yeah.
On the science, so your Andromeda, what was the range of velocities that was shown?
The range
Color
of
scale.
velocities is about 550 kilometers per second from one side of the galaxy to the other.
Right, and I seem to remember the approach velocity. of that
About
was
300.
about 300.
300, yeah.
Okay, so do you get that out of this exercise?
Yeah, now with the Andromeda one, we're kind of telling them what frequency ranges to map. And from that information we gave them, they can calculate. They could also take a spectrum of Andromeda like I showed you. But we try to, all these can become more complicated if we want to. So with the Andromeda one, it's more about visualizing the color and given the frequency bands that we gave you,
Yeah.
calculate these things. But then we switch into okay, now let's do farther away galaxies that you can't resolve. We're gonna do on-off spectra, and then, there are no frequencies in advance. They're measuring them from the spectrum. So they get the lesson eventually.
Okay, thanks.
That's just the radio. The optical's fantastic. So I hope to see you in some of the other talks as well. Thanks, everyone.